Hi all, in this video we are going to build a miniature transformer model entirely from scratch using TensorFlow and Keras. We'll generate a random dataset, implement token plus position embedding, and then we're going to define a transformer encoder block, train on synthetic data, and then we're going to visualize what our model learns. By end of this, we'll have building blocks to customize our own transformers. So first up, we ensure TensorFlow is installed. Here we are using TensorFlow 2.18 version. Then we import the required libraries, NumPy for data creation, Matplotlib for plotting results. And then we're going to generate synthetic dataset. To keep things lightweight, we generate random integer sequences of length 100. So each token is a random int between 0 and 2000. Our labels y are also random. Picking class 0 or 1, we split it into 800 training samples and 200 for validation. And then we're gonna do token and position embedding layer. Here this is our custom layer. The embedding layer maps each token ID to a dense vector. We also learn a separate positional embedding for each position in the sequence. Because transformers have no inbuilt notion of token order, in call we look up both embedding and add them element-wise, yielding a combined representation of token plus position for each time. And this is a transformer block and transformer and product block. We apply multi-head self-attention over the inputs, drop and add residual connection, and then apply layer normalization that gives us out one. We follow with a two-layer feed-forward network and also with another residual plus norm, and it's done. So this encapsulates the core of original transformer encoder. After that, we're gonna assemble the model. Here we put it all together. Input tokens go through our embedding layer, then a single transformer block. We pool across time with global average pooling 1D and add a couple dense dropout layers, and finally output a softmax over our two classes. So the model summary call prints the architecture, so we can verify the parameter counts. After that, we're going to do compiling and training. We compile the Adam optimizer and sparse categorical cross entropy since labels are integer encoded. And then we train for 5 epochs with our synthetic dataset. And we're going to plot the validation accuracy once training and validation accuracy. Once training finishes, we plot both of these over epochs. We'll in general see overfitting or underfitting. So to test our model, we generate a random test sequence and run model predict. We take the Rmax to pick the predicted class and print the class plus its softmax probabilities. So it's often helpful to see the probability distribution. Here we draw a bar chart so we can visually inspect how confident the model is. After that, TSNA of learned embeddings. So we grab the penultimate layer 20-dimensional output, reduce them to 2D with SNE and plot the points colored by true label. So this gives us an intuition of how separable the class are in embedding space. And finally, we compute the model's confidence, the max of max, and the entropy to measure uncertainty. We also list the top k class probabilities, which is useful when we have more than two classes. And then to wrap up, we create a 3-toy sentiment sequence, one negative cluster of low IDs, one positive cluster of high IDs, and a mix. And then we run inference and print out what the model thinks in our synthetic settings. It is not, but we can see exactly how we can apply real tokenized text. Thank you. So next, we're gonna look into fine-tuning a pre-trained transformer. So we will be fine-tuning BERT for IMDb sentiment classification. So we'll be using a BERT model on the IMDb movie review dataset using TensorFlow, Keras NLP, and Hugging Face Transformers library. By end of this code, we'll evaluate accuracy, plot a confusion matrix, inspect confidence distributions, and even diagnose misclassified examples. So we'll install the three key libraries, which are Keras NLP for Keras active native NLP utilities, and then TensorFlow datasets to load IMDb dataset easily, and then transformers for the TensorFlow BERT implementation and tokenizer. The -q flag keeps the output clean. Next, we import everything we need, Keras NLP and TFDS for data, and TensorFlow core, NumPy, and BERT tokenizer to encode text, and create optimizer for warm-up schedule. Finally, matplotlib and Seaborn for plots, plus scikit-learn for metrics. Then we're going to load the IMDb dataset. Using the TFDS, we load the IMDb reviews. We're going to split 80% for training and 20% for validation. As supervised is set is true, which gives us text comma label as pairs, and the test split is induced here. And initializing the BERT tokenizer. Here we pull in the uncased BERT tokenizer. This will lowercase text and split on word piece tokens. Matching the pre-trained weights, we'll load next. Then we're going to do tokenization and encoding function. So this is our function. So we define tokenized dataset to loop over each of the text comma label pairs, decode bytes to string, and call tokenizer.encode plus. We force each example to length 128 with padding or truncation, and then we're going to collect input IDs and attention mask and labels them to convert lists to NumPy arrays. So this pre-processing can take a minute, considering caching or using TF.data pipelines for production environment. And then we're going to load the pre-trained BERT model. Now we initiate the BERT for sequence classification from pre-trained BERT base and case checkpoint, specifying num labels equal to 2. For binary classification, Hugging Face take care of the model layers plus a classification head, and then we'll be configuring optimizer and learning rate scheduler. We'll train for 3 epochs with batch sizes 32, and then we calculate the steps per epoch. Total training steps and warm-up steps define 10% of total, and create optimizer returns a Adam optimizer with a linear warm-up followed by decay, standard for fine-tuning BERT. And then we're gonna compile and prepare TF datasets. We compile using a custom optimizer, sparse cross entropy, single labels are integer, and track accuracy. Then we wrap inputs and mask into tf.data.dataset, and we're gonna shuffle training, batch both sets, and it's now ready for model fit. Moving on to training and evaluation, we're gonna train for 3 epochs. Will take roughly around 15 to 20 minutes. Afterwards, we call model.evaluate on the validation set and print loss and accuracy. So here we got approximately the accuracy as 0.88%, 88%. Then we're gonna do confusion matrix and classification report. So then next we predict the logits, take argmax for predicted labels and stack true labels. We then plot a confusion matrix with Seaborn. Note where the model confuses positive versus negative. Then we print press and recall and F1 scores per class. It's usually great for spotting class imbalance or bias. Then moving on to confidence distribution and calibration. Here we convert the logits to softmax probabilities, extract each sample max score as confidence, and plot its distribution. Then we bin confidences into 10 buckets and compute the actual accuracy per bin. This calibration curve shows whether high confidence predictions are truly reliable. And then finally, let's look at some of the misclassified examples. We list the first few review indices where predictions are not equal to true. Therefore, print the true versus predicted labels and confidence. Shows them as text expert excerpt. So this error analysis is invaluable for understanding the model's blind spots. So this wraps up our fine-tuning BERT on IMDb reviews. We have done pre-processing, optimizer, scheduling, training, evaluation metrics, calibration, and error analysis. Thank you. Next, moving on to inference with a pre-trained classifier. Here, we're going to do quick sentiment inference with Keras NLP BERT classifier. We load a ready-made BERT sentiment classifier from Keras NLP, and then we're going to run inference on sample sentences, visualize the outputs, and measure runtime. No training required. It's perfect when you just need quick predictions. So firstly, we install Keras NLP, and then we import the Keras NLP itself and TensorFlow, NumPy, and Python time module, so we can benchmark inference speed. That's for the setup. And then next we call BERT classifier dot from present BERT base English model. So this downloads a 108 million parameter English BERT model prepared for text classification. And then we specify number of classes as 2 for binary sentiment. Under the hood, Keras NLP bundles the tokenizer, preprocessor, and backbone and head into one neat object. So we prepare a small list of 17 movie review snippet that mix praise and criticism. So this diversity ensures we test the models across happy, sad, and other emotions, sentiments. So a single predict calls returns raw logits for each text one score per class. You can see the values minus 0.7 comma minus 33. Higher logits means the model leans towards that class, therefore index 1 is set as positive. So the classify text function, to simplify, we write this function to call predict on a single string and then apply softmax to convert logit into probabilities and choose class 1 as positive if its probability is higher. Now we get human readable output, and then we loop through each example, print the text, the predicted label, and the two value probability array. And then we also try 5 custom user supplied sentences. This shows how exactly to integrate the classifier into your own app. And then we're going to do model summary table, highlight the tokenizer vocab, backbone parameters, and classifier head parameters, which is around 1.5k. So a quick summary call reveals the full pipeline, the tokenizer preprocessor, and the 108 million parameter BERT backbone, and also the droplet and head with just 1.5k parameters. Everything is wrapped in one Keras model. So how long to predict 17 samples? On this Colab GPU, it's about 2 seconds. Knowing the runtime is crucial for real-time applications. So to make more visual, we loop and draw bar charts per sentences. We can get an intuitive sense of model's confidence in each class. And then as a sanity check, we assemble 5 labeled examples and compute accuracy. Here it's only 40%. Remember that it's a pre-trained generic classifier, may not perfectly match your domain. Fine-tuning or prompt engineering might be needed for production use case. And finally, we package everything into batch classify that returns a list of text, label, and probability as a tuple. Drop this into your pipeline, and it's ready to classify any array of strings in one shot. Thank you.